The number that supposedly proves ancient humans lived short, brutal lives 35 years describes almost nobody who actually lived in the ancient world. It is a statistical ghost, conjured by averaging the deaths of infants who never saw their 5th birthday into a figure that was then mistaken for a typical human lifespan. And the skeleton that exposes this mistake most cleanly has been lying in the ground in central Portugal for approximately 9,000 years. In 2018, a team of archaeologists working a Mesolithic-Neolithic transition site in Portugal uncovered a man who had lived sometime around 7,000 BCE. The bones were well preserved, cool earth, stable conditions, 9 millennia of patient stillness. The team ran the standard forensic battery: pubic symphysis degeneration, auricular surface changes, cranial suture closure, each method reading biological aging written into bone, each producing an independent estimate of how long this person had been alive when he died. Every method pointed to the same place: late 60s, possibly early 70s. The team sat with that for a moment. What made the bones impossible to look away from was the physical record inscribed in them, a record of a life that had been long and hard and kept going anyway. His hands told the first part of the story. The arthritis was severe, not the mild stiffness of early middle age, but the deep, deforming joint disease that develops over decades of accumulated strain. The bone had lipped and remodeled around every joint, the surfaces distorted into shapes no healthy hand produces quickly. His spine offered a different chapter: compression fractures in the lower vertebrae, consistent with carrying heavy loads across many years, the slow accumulation of force pressing down through the same column of bone season after season until the bone itself yielded and compacted. Then the ribs. Healed fractures multiple, the breaks long since knitted into solid bone. Fractures like these heal only under specific conditions. The person must be kept still, kept fed, kept warm. For bone to bridge a break cleanly, no infection, no displacement, no catastrophic re-injury. Weeks pass, sometimes months. During all of that time, this man could not hunt, could not gather, could not carry water or work the grinding stone. And yet the breaks healed. Someone made sure of it. He was lying on his side when they found him, positioned with care that did not look accidental. The posture of sleep, not the collapsed, disordered arrangement of a body thrown or abandoned, but the deliberate placement of someone loved or honoured, or both. Beside him, a grinding stone. Worn smooth. Not freshly made, not placed as a symbol of wealth or power, but an object that had been used, worked by human hands over a long time until the surface told its own story of sustained contact. Someone chose this particular object, this worn and familiar thing, to go into the ground with him. Think about what that choice means. Of all the objects that could accompany a body, someone selected one that had already given years of service. One that carried, in its smooth surface, the evidence of work done across time. It is not the gesture of people who expected life to be brief, and yet the figure that defined how most people, and for much of the 20th century, most scholars imagined ancient human existence, said this man should not have been here. The number is 35. Life expectancy at birth in the ancient world, we are told, was approximately 35 years. Neolithic people, in this version of history, lived hard and died young, perpetually inexperienced, perpetually at the beginning of things. And yet this man had arthritis so advanced it had deformed his joints, spinal compression consistent with decades of load-bearing, and rib fractures that required weeks of immobile convalescence to heal. His skeleton read, to every forensic analyst who examined it, as the body of someone in his late 60s or early 70s. The question is not why he survived so long. The question is why we ever believed he shouldn't have. And that answer starts with a number, a single figure that has been doing the work of a description while functioning as nothing more than a statistical artifact. 35 years. That number appears in textbooks on 6 continents. Documentaries deliver it with authority. Newspaper features deploy it in the kind of confident half-sentence that signals a writer knows something about the past. Life expectancy in ancient Rome, approximately 25 to 35. Medieval Europe, 30 to 35. Neolithic prehistory, roughly the same, possibly worse. The implication is always identical. Ancient people died young, lived hard, and never accumulated enough time to become anything other than perpetual beginners in a brutal world. The number is real. It is not fabricated. It appears in the historical and archaeological literature with legitimate citation trails. It is also, as a description of how long ancient people actually lived, almost completely meaningless. A life expectancy at birth is a statistical average. Every death in a population, every infant who died in its first week, every child who succumbed to fever before age 3, every young adult killed in a raid, every middle-aged woman who died in childbirth, every 70-year-old elder who finally wore out all of those deaths, are pooled and divided by the number of people in the sample. What emerges is the arithmetic mean of the entire distribution. It does not describe the most common experience. It does not describe what happened to people who survived childhood. It describes a mathematical center radically skewed by deaths, clustered at the very beginning of life. In pre-modern societies, somewhere between 30 and 50% of all live births died before age 5. Not 30 to 50% of people eventually. 30 to 50% of everyone born alive did not survive to their 5th birthday. Roman estimates place first-year mortality alone at between 25 and 33%. Prehistoric estimates push that figure higher. Still, roughly 40% of children may not have survived their first year, though the uncertainty around that number is significant. Now do the arithmetic intuitively. Imagine 100 people born in ancient Rome. Before those 100 reach their 5th birthday, 30 to 50 are gone. Many died in their first months of life, their deaths recorded nowhere, submerged into the statistical mass. You are now averaging those lifespans, many measured in weeks or months, alongside everyone who survived. Every infant who lived 3 months and died of infection pulls the average down. Every toddler who succumbed to contaminated water before age 2 pulls it down further. Pull hard enough, with enough deaths clustered at 0 and 1 and 2 and 3, and the average lands somewhere around 35. Even if every person who survived past age 5 went on to live into their 60s, that is not a theoretical possibility. That is the mechanical consequence of applying a mean to a heavily skewed distribution. Professor Walter Scheidel, a historian at Stanford who has spent years working through Roman census data, Egyptian papyri, and the skeletal record, states the conclusion directly. As soon as you remove the infant mortality from the equation, life expectancy for adults in the ancient world was not dramatically different from what we see in pre-industrial societies today, which is to say, people who made it to 15 could expect to live into their 60s and sometimes their 70s. Read that carefully. Scheidel is not saying ancient life was easy. He is saying that once you remove the catastrophic mortality of infancy and early childhood, the underlying adult lifespan looks recognizably modern, into their 60s, sometimes their 70s. The 35-year figure does not describe those people, not even close. Christine Cave, an archaeologist at the Australian National University who has spent years applying forensic methods to ancient skeletal material, states her conclusion without qualification. The idea that nobody lived past 40 inches the past is just wrong. Not probably wrong. Not wrong in some statistical sense requiring careful qualification. Just wrong. She is also identifying something precise about why the error persisted. The 35-year figure is not simply a statistical mistake. It is load-bearing infrastructure for a particular story about human progress. If ancient people died young and hard, then modernity is rescue. The gap between then and now is vast and flattering. Challenge the number, and you challenge the story. And stories that make the present feel like an achievement are not surrendered easily. The creature being exposed here has a specific anatomy. It is not a lie told by bad historians. It is a category error, a figure calculated for one purpose, lifted from its context, and applied to a question it was never designed to answer. Life expectancy at birth is genuinely informative about population-level health, about the burden of infant and child disease, about the impact of public health interventions across time. What it cannot do is tell you how long an adult in the ancient world expected to live. For that question, you strip away the infant deaths and examine what remains. So what do the numbers actually show when you do exactly that? Start with J.P. Griffin, a physician and medical historian who published his analysis in 1995 and sharpened it in 2008. Working through pre-industrial demographic records with the specific purpose of separating childhood mortality from adult lifespan. Once the deaths of children who never reached their 5th birthday were set aside, life expectancy at age 5 was 75 years for men and 73 years for women. 75, 73. Numbers that would not look out of place in a contemporary public health report for a developed nation. Griffin's work was not an outlier. In 2007, anthropologists Michael Gervin and Hillard Kaplan published a landmark cross-cultural analysis in Population and Development Review. Their study examined modern hunter-gatherer populations living under conditions broadly comparable to those of prehistoric humans, the Hadza of Tanzania, the Aceh of Paraguay, the Kungsan of the Kalahari, the Tsimane of Bolivia, and asked what happened to adults in these populations when violence, accident, and specific acute infections were not the cause of death. Their answer: an adaptive human lifespan of 68 to 78 years, the same bodies, the same biology, the same genetic architecture every human carries, and when given the chance to wear out naturally, they wore out in their late 60s or 70s. The Hadza data makes the statistical mechanics vivid. Life expectancy at birth for the Hadza is approximately 33 years, the number that would appear in a textbook if someone applied the standard methodology. But a Hadza individual who survives to age 20 has a remaining life expectancy of approximately 39 additional years. A 20-year-old Hadza adult can statistically expect to reach roughly 59. Not 33, not 35, 59, and that is the average. Meaning substantial numbers of individuals are dying considerably older, pulling the figure toward its upper end. The 33-year figure and the 59-year figure describe the same population. They just answer different questions. The Roman skeletal evidence says the same thing in calcium. An analysis of Roman-era skeletal samples spanning from 100 BCE onward, multiple sites, thousands of individual remains, filtered to exclude juvenile deaths, found a median age of death of 66. More than half of all Roman adults who cleared childhood died at 66 or older. Bruce Fryer's reconstructed Roman life tables, published first in 1982 and refined through subsequent work, allow a still more specific calculation. A 10-year-old in the Roman world could expect to live approximately 48 to 50 more years. Add 10 to 50, and a Roman child who had survived the gauntlet of early life was statistically aimed at 60. The modal age at death, not the mean, not the median, but the single most common age at which adults died, was consistently in the 60s and 70s across cultures, centuries, and methods. Griffin found it. Gervin and Kaplan found it in the living descendants of prehistoric foragers. The Roman skeletal record found it. These are independent lines of evidence, working from different source materials, different methodologies, different disciplines, converging on the same range. Ancient adults, like modern adults, most commonly died old. Now hold that finding against the outer biological limit. Gorgias, a Greek philosopher born around 483 BCE in Leontini, Sicily, died in 375 BCE. That is not a skeletal estimate. It is a historical record, preserved in multiple ancient sources, describing a man who lived to approximately 108 in the 5th and 4th centuries BCE without antibiotics, without surgery, without any medical infrastructure we associate with longevity. The outer edge of human biological potential was the same in antiquity as it is today. Jean Calment, who died in 1997 at 122 years and 164 days, holds the verified record, and researchers studying the biology of human aging have found no compelling evidence that sealing has shifted across historical time. It was available in Neolithic Portugal. It was there when the man with the grinding stone was buried. The question was never whether the biology permitted long life. It was always whether any given individual survived long enough to use what the biology had always been capable of producing. The ghost number dissolves when you look at the actual data. What replaces it is considerably more interesting and considerably more human. A past populated not by perpetual beginners dying before they could accumulate anything worth knowing, but by communities that contained, regularly and predictably, individuals who had been alive for 6 decades or more. There is a moment in every forensic analysis of an ancient skeleton when the scientist stops looking at the person who died and starts reading the calendar the body kept. Bone ages, not metaphorically biologically. And for researchers working with remains thousands of years old, the aging of bone is the only clock available. The methods are specific and painstaking. The pubic symphysis, the joint at the front of the pelvis in young adults, is ridged and rough like corrugated terrain. Decades wear those ridges flat, break down the edges, develop a characteristic pitted surface. The auricular region of the pelvis undergoes its own progression, increasing texture, granularity, densification. Cranial sutures, wide open in infancy, fuse through adulthood in a mapped sequence. Dental wear measures something different. Not internal deterioration, but the accumulated mechanical record of a life lived. Every meal ground between molars, every decade of chewing inscribed into enamel surfaces. Together these methods form a multi-source diagnostic. No single indicator is trusted alone. A competent analysis cross-references all 4, looking for convergence. This is not guesswork. It is disciplined inference from physical evidence. It is genuinely remarkable that it works at all. Then, in 1982, 2 French researchers published a paper that stopped the field cold. Jean-Pierre Bocquet-Appel and Claude Masset published Farewell to Paleodemography in the Journal of Human Evolution. Their argument was direct. The methods bioarchaeologists use to estimate skeletal age at death are so imprecise, particularly for individuals over 50, that demographic reconstructions built on those estimates are essentially unreliable. This was not a minor technical quibble. It was an attack on the evidentiary foundation of everything the field had been building for decades. The specific problem was reference sample bias. Every aging method must be calibrated against known individuals, bodies whose age at death is documented, so analysts can build statistical models translating bone morphology into age estimates. The Terry collection at the Smithsonian, assembled between 1898 and 1967, contains approximately 1,700 skeletons, predominantly from older individuals who donated their bodies to science or died in institutional settings. The Spitalfields collection provides a European counterpart. Both are real, documented, scientifically valuable. Both are also systematically skewed toward older adults in their age distribution. When you calibrate an aging method against a reference sample weighted toward the elderly, your method learns to push estimates toward older ages. Apply it to an ancient population with a genuinely different age structure, and the estimates are wrong in a systematic, predictable, and very difficult to correct direction. A practical consequence follows directly. A skeleton assigned by multiple methods to approximately 60 carries an error range spanning plus or minus 15 to 20 years. The true individual could have been 45, could have been 75, the method cannot reliably distinguish between them. Precision improves for individuals estimated under 40. The biological markers change more rapidly through young adulthood, but for the individuals who matter most to this argument, the method becomes dramatically less discriminating at exactly the ages where the question is most consequential. The field absorbed this critique. Lyle Koenigsberg and Susan Frankenberg developed Bayesian statistical approaches in the early 1990s, specifically designed to address reference sample bias. The Bayesian framework incorporates prior information about likely population age structures into estimates, correcting for the distortion Bocchet-Appel identified. It is a genuine improvement. Koenigsberg and Frankenberg were clear, however, that the correction improves the estimate without resolving the underlying imprecision. The biological aging process these methods read is real, but variable individuals age at different rates, their bones and teeth reflecting different combinations of genetics and lived experience. Bayesian statistics can manage reference sample bias. They cannot eliminate biological variability. The critique was absorbed. It was never fully refuted. Christine Cave's research sits at exactly this fault line, applying a refined dental wear method to skeletal samples from Anglo-Saxon and Roman British burial sites in England. She found that adults in these communities routinely survived into their 60s, 70s, and occasionally their 80s. Her finding aligns with everything Griffin and Girvan and Kaplan established through independent roots. The criticism it attracted was equally legitimate. Dental wear rates are not purely internal biological processes. They are the product of the interaction between teeth and food. A population eating coarsely ground grain from millstones whose surfaces shed grit into the flour wears its teeth dramatically faster than one eating softer foods. Cultural practices using teeth as tools for leatherworking or sinew processing alter wear rates independently of age. Two individuals of precisely the same biological age, eating different foods in different cultural contexts, will present wear patterns the method assigns to different decades of life. Whether Cave is capturing real longevity or a dietary and cultural context that accelerated wear has not been definitively resolved. Her findings have not been retracted and have not been refuted outright. They have not achieved methodological consensus either. James Wood, George Milner, Henry Harpending, and Kenneth Weiss deepened the problem further with their 1,992 paper in Current Anthropology, The Osteological Paradox. It identifies three interlocking problems beneath all bioarchaeological reconstruction. First, selective mortality. The dead in any burial site are not a random sample of the living. Those who die young may have been more biologically frail. Those who die old were, on average, more biologically robust. The skeleton of an elderly individual and the skeleton of a young individual are not equivalent data points. They are the outputs of a process that selected against frailty at every stage. Second, hidden heterogeneity and frailty. Two skeletons showing identical pathological lesions may represent completely opposite stories. One person who died young because the lesion reflected underlying weakness, another who died old despite it. Identical markers, opposite meanings. The skeleton offers no reliable way to distinguish between them at the individual level. Third, demographic non-stationarity. Ancient populations were not closed, stable systems. They experienced epidemics that killed from specific age cohorts, famines that raised mortality unevenly, migrations that altered the age structure recorded in any given cemetery. The mathematical models used to interpret burial assemblages assume demographic stability that ancient communities never maintained. The osteological paradox does not say bioarchaeology is impossible. It says every conclusion about ancient longevity must engage explicitly with what selective mortality, hidden heterogeneity, and demographic fluctuation might be doing to the pattern observed in the bones. Here is the position the evidence requires. The record contains individuals who unambiguously died old, whose bones show advanced degeneration, accumulated healed injuries, and severe arthritis that require decades to produce. That record is documented across multiple sites, multiple periods, multiple independent research teams. The convergence across methods and geography is meaningful. At the same time, every specific age estimate carries genuine uncertainty. Every skeleton assigned to the late 60s or early 70s might have been 50, might have been 80. The methods that produce the estimate are the best available and honestly imprecise at exactly the ages where the argument is most consequential. Science does not always offer clean conclusions. Sometimes it offers a convergence of imprecise but independent lines of evidence pointing coherently in the same direction, while each individual line remains genuinely uncertain. That is the position this field occupies. Understanding the difference between those two things is the difference between following the evidence and simply choosing the answer you prefer. Now, go to southwestern France. 1908. A small village called La Chapelle-aux-Saintes in the limestone Corrèze, where rock shelters open along cliff faces that have provided shelter since before the word existed. 3 brothers are digging. Amédée, Jean and Paul Boissonny, Catholic priests and serious amateur archaeologists, had been working a site they called the Bouffia Bonneval, a shallow rock shelter barely 5 meters wide. In August, roughly half a meter below the surface, their tools found bone. Not scattered bone. A skeleton, largely intact, lying in what appeared to be a deliberate depression, a hollow the body fit into as though placed there, skull present, mandible present. Long bones, ribs, vertebrae, all in rough anatomical position, preserved by cool darkness through 50 millennia. They understood immediately. This was the most complete Neanderthal skeleton ever found. They sent it to Paris. To Marcelin Boulay. Boule was not merely a leading paleontologist. He was the director of the Institut de Paléontologie Humaine, the most prestigious human origins researcher in France and arguably in the world. When Boulay spoke about a fossil hominid, textbooks listened. Museums built their dioramas. Artists sharpened their pencils. He worked on the La Chapelle skeleton for 3 years. He published his analysis in 3 meticulous volumes between 1911 and 1913. His conclusion was vivid. The creature had walked bent over, Boulay argued. The spine curved forward in a permanent stoop. The head thrust out from the shoulders at an animal angle. The knees were permanently flexed, incapable of full extension. The feet were divergent, grasping more like a great ape moving awkwardly across open ground than a human striding. The brain, though large, showed frontal lobes underdeveloped, and occipital lobes dominant the neurological signature of a creature ruled by sensation and reflex, rather than abstraction and language. Not quite human. Something crouched and dark and halfway between apes and moderns. That image spread with the efficiency of a scientific consensus. Within a decade, it was in every major textbook. Museum halls from Paris to New York built reconstructions from Boulay's specifications. The bent back, the flexed knees, the thrust-forward skull, the hairy, hunched silhouette that would haunt popular imagination for generations. 50 years passed. In the 1950s, American anatomist William Strauss sat down with the original La Chapelle bones. He was joined by British anatomist A.J.E. Cave, and together they went through the skeleton the way a physician reads an X-ray series, looking not just at what was there, but at what it meant. What they found was not a primitive stooped posture. What they found was arthritis. Severe, advanced, degenerative arthritis of the spine, the kind that develops across decades of load-bearing, of repetitive strain, of a skeletal system gradually surrendering to the accumulated mechanical insults of a long and physically demanding life. The vertebrae showed characteristic deformation, bone growths, joint space narrowing, the compressed architecture of a spine that had been carrying a body for a very long time. The curved posture Boulay read as evolutionary primitiveness was the posture of an old man whose back hurt. The thrust-forward head was the posture of someone whose neck vertebrae had degenerated to the point where holding the head fully erect was painful, perhaps impossible. The skeleton had stood upright in life. Fully, normally, completely upright. As upright as you are right now. Boulay had looked at the pathology of aging and read it as evidence of evolutionary inferiority. He had taken a medical condition, one any modern clinician would recognize within minutes, and reinterpreted it as a statement about a species. The foundational image of Neanderthal primitiveness was built from the arthritic remains of a body that had simply grown old. The revision entered the literature. Textbooks were updated, slowly. Museum reconstructions were eventually corrected. But something else was buried in the La Chapelle skeleton that took longer to appreciate. Look at where the teeth should have been. The old man had lost most of his teeth before he died, not at death, but earlier, during his lifetime. Through the gradual attrition that accumulates across decades, the crucial detail is not the absence. It is what the jawbone did in response. When a tooth is lost, the alveolar bone, the socket that held the root, does not stay as an empty hole. It remodels. The bone fills in, smooths over, the socket closing as the jaw responds to the changed mechanical environment. This takes months. In the La Chapelle skeleton, multiple sockets had undergone this remodeling. The jawbone had healed over spaces where teeth had been. The bone surface smooth and rounded. The original socket architecture entirely obliterated. Now think about what that means practically. A Neanderthal diet was not soft. Isotopic analysis, cut marks on animal bones, starch residues on ancient tools all point to food that required teeth. Meat, roots, wild plants with fibrous structures. An individual with no teeth in a Neanderthal band in Pleistocene France could not independently process that food. Someone was doing it for him, chewing meat to soften it, grinding plant material into a form he could swallow, not as a one-time gesture, as a sustained daily arrangement, continued for months or years while the jawbone healed its sockets and the old man continued to live. Eric Trinkhaus, one of the most eminent paleoanthropologists working today, framed the evidence with precision. The specimen that gave us our image of Neanderthals as brutish and primitive was actually an old, arthritic, toothless man who lived to an advanced age because his community took care of him. Read that again. The specimen that built the brutish image was the strongest possible evidence against it. The old man was approximately 40 years old when he died. By modern standards, barely middle age. But he was living in Pleistocene Europe, where infection could kill within days of any wound, where a broken bone without intervention was often a death sentence, where every year of survival represented a body that had successfully navigated hazards that claimed many contemporaries. At 40, with severe spinal arthritis, with most of his teeth gone, the old man was genuinely old, and someone had kept him fed while that happened. The bitter precision of the irony cannot be overstated. Boulay examined the one Neanderthal skeleton that demonstrated, with more clarity than perhaps any other specimen of the period, that these creatures possessed exactly the social capacity his reconstruction denied them, the capacity to care for the old and incapacitated, to sustain members of the group who could no longer fully sustain themselves. He looked at the evidence of that social complexity and read it as evidence of biological primitiveness. He saw the arthritis of a survivor and called it the stoop of a brute. The image held for 50 years of textbooks, 50 years of museum exhibits, 50 years of the implicit cultural message that Neanderthals were fundamentally less than us. Generations of students were taught the wrong thing from the right evidence. The bones were always telling the true story. The error was in who was reading them and what they were prepared to see. Strauss and Cave's correction did not arrive as a dramatic scandal. It arrived as a methodological revision in anatomical journals, trickling into educational materials over decades. Science does not always correct itself loudly. The stooped Neanderthal entered the imagination with force. The upright, arthritic, cared-for old man of La Chapelle replaced it gradually, almost gently, without the drama the truth deserved. Iraqi Kurdistan, 1957. Ralph Selecki is working a cave called Shanidar, a vast limestone cavern in the Zagros Mountains, its mouth 45 feet high and 60 feet wide, its floor layered with the compressed debris of human habitation going back 100,000 years. In 1957, his team reaches the Neanderthal levels. Then they find him, lying on his left side, knees drawn slightly up, the posture of sleep. Selecki's team uncovers the skeleton carefully, documenting position and context before anything is moved. They give him a name, Nandi. What the forensic analysis eventually produced was not a single dramatic injury. It was something far more startling, a body that had accumulated damage across a lifetime and survived it. Each healed injury represents not just a wound, but a story, a moment of catastrophe, followed by enough time to recover, which means enough people and enough commitment to make recovery possible. Start with the face. The left orbital bone, the bony arch around the eye socket, had been crushed. The damage was severe enough that analysts concluded Nandi was almost certainly blind in his left eye, or had severely compromised vision on that side. The bone had healed, the fracture lines had knitted, but the architecture of the orbit never fully restored the deformation permanent, visible 50,000 years later. He navigated the world with half his field of vision gone. The right arm. Below the elbow, there is nothing. The radius and ulna are absent. What remains is the distal end of the humerus, its surface smoothed, rounded, remodeled by years of use without the structures that should connect to it. Whether this represents traumatic amputation or functional loss from a severe crush injury, the forensic record cannot definitively say. What it can say is that the bone end healed, that it was used, that Nandi lived for years, possibly the majority of his adult life, with one functional arm. The right leg shows separate trauma, damage consistent with a significant wound to the lower limb, substantial enough to have permanently altered his gait, not the minor favouring of a recently twisted ankle, a structural deviation that announced itself in every step, accumulating secondary strain across the hip and lower back across years of compensated movement. Healed rib fractures, more than one, from high-energy blunt trauma, a penetrating shoulder injury consistent with a projectile strike, the bone surface showing the healing response of tissue that had closed over an earlier violation, closed over, scarred, survived by enough margin that bone had time to respond. And then the ear canals. Bony growths inside both ear canals, dense nodular formations that develop in response to repeated cold water immersion. The same growths that form in swimmers and divers, substantial enough to narrow the canal, substantial enough to partially block sound transmission. Blind in his left eye, partially deaf, missing his right forearm, walking with a permanent limp. Carrying healed rib fractures and a healed shoulder wound as additional chapters in the same accumulating record. He lived to somewhere between 35 and 45 years. Hold that figure. Not because it sounds long, it does not, by any modern standard, but because of what it required, because of what had to be true about the world around Nandi for those years to accumulate at all. Someone fed him, literally hunted animals, or brought gathered food, and ensured Nandi received a portion. In a subsistence context where caloric intake is directly tied to physical labour output, his contribution to his own food supply must have been severely limited. Someone made up the difference, not once, not occasionally. As a sustained, habitual arrangement, someone moved with him. The terrain around Shanidar Cave is limestone karst, irregular, fractured, demanding country where footing requires full visual attention. A half-blind man with a severe gait abnormality does not move safely through that landscape alone. Someone positioned themselves near him, provided a guiding hand at difficult crossings. Not companionship in any casual sense. Physical assistance made available reliably across years. Someone defended him. An individual with compromised senses and limited mobility cannot adequately monitor his environment for threat. He needed others to extend their vigilance over him by proximity, or he needed to remain close enough that their awareness covered him. Either way, sustained commitment. In 2017, Trinkaus and colleagues returned to the Shanidar-1 material with decades of additional comparative data. Their published assessment was precise. The survival of this individual for an extended period following his injuries indicates that these Neanderthals provided sustained support to a disabled member of their social group. Sustained. That word is doing significant work. Not episodic support, not crisis intervention followed by abandonment. Sustained, continuous, habitual, organized over years into the ordinary fabric of how this community functioned. Nandi's survival was not an accident of his own robustness. It was the product of a social arrangement that persisted long enough for a crushed orbital bone to heal, for a missing forearm to develop a smooth, rounded terminus, for fractures to consolidate, for a penetrating wound to close over. There is a claim that circulates in discussions of this kind of evidence, often attributed to Margaret Mead, often cited in anthropology seminars. The story goes that a student once asked Mead what she considered the first sign of civilization. Not writing, not agriculture, not tools. Her answer was a healed femur. A broken leg, because in the wild, a broken leg means death, and a healed femur means someone stayed. The attribution is contested, but the archaeology does not need it, because the archaeological record makes the same argument on its own authority. Healed fractures appear in the human and hominin fossil record going back hundreds of thousands of years. Shanidar-1, La Chapelle aux Saints, dozens of other specimens from dozens of other sites across Europe and Asia and Africa. These are not rare events. They are the standard condition of ancient bones bodies that broke and were held together long enough to heal, which means bodies that were held together by other people. Pat Shipman, a paleoanthropologist whose career has focused on the behavioral implications of fossil evidence, put the inference in terms that collapse the distance between 50,000 years ago and now. The evidence shows that care for the injured and elderly is one of the defining features of our genus. Not one civilization, not one culture, not one period. The genus, the entire lineage. Nandi was not alone. That is the sentence the evidence keeps writing. Across continents and across millennia, in burial pits and shell middens and canal excavations and Bronze Age cemeteries. Start in southern Sweden. The site is Skateholm, a Mesolithic and early Neolithic burial complex on what was once a coastal lagoon, occupied from approximately 6,000 to 4,500 BCE. Archaeologists excavating the site in the 1980s under Lars Larsen recovered more than 80 individual burials. Among them, a man in his 60s, placed with deliberate attention beside a child positioned in close proximity, a pairing that signals intention rather than coincidence. Antlers. Tools. Objects that required effort to acquire and effort to include. In the material economy of a Mesolithic community, where every usable item had a replacement cost measured in labor and skill, burying tools and antlers with a body was a statement. The community was spending social capital on the memory of one of its members. The man was old. The community had apparently decided that his oldness was something worth marking. This is 6,000 BCE. Before the pyramids by 3.5 millennia. Before writing. Before any institutional architecture of religion or governance we can identify by name. Move forward roughly 2,000 years and several hundred kilometers west. The Netherlands, around 3,700 BCE. A Neolithic burial field, studied by researchers at Leiden University and published in 2022. When they analysed the distribution of grave goods across the burial population, a pattern emerged that was, in their own assessment, unexpected. The elderly women had the richest grave goods, not the young, not the physically powerful, Not the individuals in prime reproductive years that evolutionary logic might predict would accumulate the most social investment. The old women. The researchers' published conclusion was measured but unambiguous. There appears to be a certain status associated with age. In less guarded terms, a community that left no written records encoded, in the objects it placed in the ground, the old women were worth the most. Now, go south. Austria. Franzhausen, in the Lower Austria region, a Bronze Age cemetery containing hundreds of burials spanning approximately 2,000, 200 to 1,000, 400 BCE. 6 centuries of continuous burial practice laid out in a single accessible record. At the beginning of the sequence, elderly individuals are buried in graves resembling their neighbours, ordinary arrangements, ordinary goods, nothing marking them as particularly significant in the social hierarchy. By the end of the 600-year span, that had changed completely. Elderly individuals had moved from ordinary graves to prominent positions. Their grave goods were richer. The researchers described the elderly, by the later period, as having become leaders of society. 6 centuries of a community, gradually encoding through its burial practice that the old were not simply survivors of time, but its stewards. These 3 sites, Skateholm, the Netherlands Field, Franzhausen, already span 4,000 years and 3 distinct cultural contexts. But none of them is the most arresting piece of evidence in this argument. That belongs to Bad Dürrenberg. Eastern Germany, 1934. Construction workers widening a canal encounter something unexpected below the surface. Archaeologists are called. What they find is a double burial. A woman and an infant, curled together in physical closeness. The burial dates to approximately 7,000 BCE, the early Mesolithic, a world of foragers and hunters and seasonal movement across landscapes since transformed entirely. The woman's grave goods stop the archaeologists cold. A headdress assembled from deer antlers and boar tusks, a polished stone axe, a bone dagger, a turtle shell, the wing bones of a crane, laid with her in a way suggesting they were attached to clothing. More than 80 individual animal teeth, each perforated, each worn as decoration, the richest Mesolithic grave assemblage ever recovered in Central Europe. The crane bones, the turtle shell, the elaborate headdress, these are not markers of accumulated wealth. They are markers of a role, a function, a status that required specific objects to represent it in death. She is referred to in the literature as the Bad Dürrenberg shaman. She died between roughly 25 and 35 years of age. In 2019, a team of geneticists ran ancient DNA analysis on both individuals from the burial. The question was simple. What was the biological relationship between the woman and the infant buried beside her? The infant was not her child. The genetic relationship was far more distant. The infant was her great-great-great-great-grandson, separated by 4 or 5 generations of descent, born centuries after her death, and yet buried beside her body as though the link between them had never broken. Her family had maintained memory of her status across so many generations that when this infant died, someone made a decision. This child goes with her. Whatever she had known, whatever she had represented, it outlived her by centuries and was still considered so significant that it warranted this final act of connection between her bones and those of a child born into a world she had never seen. Move to Southeast Asia. Northern Vietnam, a burial site called Man Bac, occupied during the late Neolithic and early Bronze Age between approximately 1,500 and 1,000 BCE. Among the burials is one designated Burial 9, a male, aged roughly 20 to 30 at death, whose remains challenged every assumption the excavating team held about the social capabilities of a community at this level of material complexity. This individual had juvenile onset quadriplegia, A rare congenital condition had left him unable to use his limbs in any functional way from childhood or early adolescence. His bones showed the distinctive changes of long-term paralysis, muscle attachment sites underdeveloped from chronic disuse, joint surfaces altered by immobility, the skeletal signature of a body that had not moved under its own power for years. He had survived this condition to young adulthood. That is not possible without deliberate, sustained, organized care, not without help feeding him, managing basic hygiene, protecting him from environmental exposure. Lorna Tilley and Mark Oxenham, who published the detailed analysis in the International Journal of Paleopathology in 2011, were precise. His survival required continuous community support over years, invested in a person who could contribute no physical labor to the group's subsistence activities. The community fed him anyway, sheltered him anyway, kept him alive anyway. The interpretive debate around cases like this is genuine. In small, low-density bands, even a severely disabled individual might contribute through non-physical means tool-making with adapted techniques, childcare, knowledge transmission, ritual or social functions the community valued. Costly signaling theory proposes that caring visibly for a disabled person advertise the caregiver's resources and commitment to potential allies and partners. These explanations are not mutually exclusive. What they share is the acknowledgement that the care happened, the survival was real, the burial attention was real. Across Skateholm's antlered grave goods, the Netherlands' richly furnished elderly women, Franshausen's 6th century arc toward elder leadership, Bad Durenberg's centuries of ancestral memory expressed in a double burial, and Manbach's paralyzed young man kept alive by neighbors who expected nothing physical in return. What accumulates is not a collection of interesting exceptions. It is a civilization-wide answer to a question those communities apparently never needed to ask, because the answer was so deeply embedded in how they understood themselves. What do you do with the people who can no longer fully contribute? You bury them with antlers and crane bones and polished stone. You give them your richest grave goods. You make them leaders. You remember them across 4 generations and place your children beside them in the earth. You feed them and shelter them and keep them alive for years when they cannot stand or walk or feed themselves. You treat them as the most valuable things you have, which leaves the question the popular narrative never properly answered. If ancient adults routinely lived into their 60s and 70s, and the evidence says they did, then what was actually killing people? What compressed the averages so catastrophically? The answer is not what most people assume. Not the cold, not predators, not the relentless physical hardship of a life without modern medicine. Infection. Specifically, infection in infancy and early childhood, arriving in bodies that had not yet had time to develop immunological resistance. Ortner and Putzka, writing in 1981 inches, their foundational work on paleopathology, were unambiguous. Infectious disease was the single greatest threat to the lives of prehistoric infants and children. Not predators, not violence, not cold. Prehistoric infant mortality rates reached as high as 40% in some population estimates. Another substantial fraction died between age 1 and 5. That level of early mortality distributed across an otherwise healthy adult population, routinely reaching its 60s and 70s, produces exactly the kind of statistical average that textbooks have been misreading for a century. Ancient DNA has made the pathogen environment visible in ways skeletal analysis never could. Tuberculosis has been recovered from ancient remains across multiple continents, confirming that Mycobacterium tuberculosis was not a disease of modernity or industrialization, but a companion of human populations across deep prehistory. Rickettsia felis, a bacterial pathogen transmitted by fleas, was recovered from the skeletal remains of a South African hunter-gatherer boy who lived approximately 2,000 years ago. Toxoplasma gondii, the same parasitic organism that today infects roughly 1/3 of the world's human population, was recovered from the same individual. A single child, dead 2 millennia ago, carrying at least 2 distinct pathogens simultaneously. That is not an anomaly. That is a window into what the ancient pathogen environment actually looked like. Childbirth added a second pressure, though its contribution is more complicated to quantify. Maternal mortality was significant throughout antiquity. The physiological risks of labour and delivery, without surgical intervention, without antibiotics for postpartum infection, without blood transfusion for hemorrhage, were real. A 2014 analysis published in Science Direct found that childbirth-related death appears surprisingly rarely in hunter-gatherer skeletal samples. A finding that is either genuinely counterintuitive, suggesting that birthing practices in highly mobile forager populations may have reduced obstetric risk, or a reflection of how difficult it is to identify birth-related death in the archaeological record when the evidence may leave no durable trace. The truth is probably some of both, and the data acknowledges this rather than papering over it. Violence is harder to dismiss. A study examining 57 prehistoric individuals found that 45 showed evidence consistent with violence as the cause of or contributor to their death. Nearly 80% of the sample. If that ratio has any representativeness, and the researchers were appropriately cautious about claiming that it does, it suggests that interpersonal and intergroup conflict was a consistent source of mortality, not a marginal one. Blunt force trauma to the skull, projectile points lodged in bone, perimortem fractures with the fresh characteristics of damage sustained at or near the time of death, with no subsequent healing. What the pattern adds up to is this. The ancient world had specific, identifiable mechanisms that killed with particular efficiency at particular life stages. Infection killed the very young, before immune systems could mount a defense. Violence killed adults at any age. Childbirth took women at the moment of greatest physiological vulnerability. Accidents removed people unpredictably across all ages. But none of these mechanisms singly or combined describes a world in which adults who survived childhood were biologically fated to collapse in their 30s or 40s. None of them represents a general acceleration of adult biological aging beyond our own. Remove infancy and early childhood from the calculation and the death curve that remains looks recognizably like the curve of a pre-industrial but otherwise healthy human population. Adults dying in their 50s, 60s and 70s, some surviving into their 80s. The biological machinery was the same as ours. The outer limits of the possible were the same. The difference was in specific hazards concentrated at the most vulnerable end of the life course, the months and years when the immune system was still learning the alphabet of the pathogen environment it had been born into. The gauntlet was real. The early death toll was catastrophic in ways genuinely difficult to comprehend from the vantage point of modern pediatric medicine. But the people who came through it, who built immunity, accumulated strength, learned the rhythms of the landscape and the behavior of the things that could kill them, those people had every biological reason to grow old. And the evidence of how they did exactly that is buried across a continent of carefully tended graves. Now think about what surviving infancy actually brought you. Not safety, not comfort, not a guaranteed path to anything. What it bought was time. And in a world without writing, without archives, without any mechanism for preserving knowledge except the living mind that held it, time was not merely a personal resource. It was a communal one. Every year, an elder survived past the age. The standard narrative said ancient humans perished was another year of accumulated observation, another season of pattern recognition, another layer added to a body of knowledge no younger person could replicate or replace. An elder was a library. And that ancient world had no other way to build one. Richard Lee spent years in the 1950s living alongside the Kungsan in the Kalahari Desert, watching how a foraging community actually organized itself and actually survived. What he observed during the dry season, the months when food became critically scarce, and the landscape offered almost nothing visible to anyone who hadn't spent decades learning to read it, was not what the standard narrative of brutal, short prehistoric lives would have predicted. The older women outperformed everyone else. Not the strongest adults in their physical prime, not the fastest runners or the sharpest-eyed hunters, the grandmothers. Women who had spent so many seasons in that landscape that it had become legible to them in ways it was not legible to anyone younger. They knew where deep-buried tubers lay invisible beneath the cracked, dry surface plants with no above-ground sign during drought, their presence known only to someone who had watched the same patch of ground through enough wet seasons to remember what grew there before the water disappeared. They remembered water sources that filled only in certain unusual rains, events that might occur once or twice in a decade, the kind of thing a person in their 30s might never have witnessed. Lee summarized what he observed with precision. The knowledge of the elders was the community's library. That phrase is not rhetorical flourish. It is a functional description of an information storage system. The detailed ecological knowledge held by the senior members of these communities, which plants cured fever and which plants killed, which soil conditions favored, which crops in which years, where the river ran deep in a dry year, cannot be acquired from a single encounter or even from a decade of casual observation. Ethnobotanical studies conducted across multiple indigenous cultures converge on a consistent figure. The deep traditional knowledge held by the senior members of these communities typically requires between 30 and 50 years to acquire fully, not to begin acquiring, not to have a working familiarity, to possess it with the depth and precision that makes it genuinely reliable in the moments when reliable matters most. This knowledge does not transfer in a single teaching session. It accumulates across decades of direct observation and transmits through years of proximity between an elder and a learner young enough to hold what they are being given for another generation. Which means that for this knowledge to exist at all, the person who holds it must have lived long enough to build it, and for it to continue existing, that person must survive long enough to pass it on before they die. The same organizational logic appears on the other side of the planet. Among the Hadza of Tanzania, elderly individuals hold migration records of animal populations observed across 50 years of seasonal movement, deviating in drought years in ways only someone who witnessed the last comparable drought could anticipate. Among the Inuit of the Arctic, where misjudging ice conditions can be immediately fatal, elder knowledge of ice formation, wind behavior in specific landscapes, and the signs that precede the particular storms that kill was not supplementary information. It was survival infrastructure. Gervin and Kaplan, in their 2007 analysis, made an argument about human longevity that follows directly from this logic. They proposed that the human lifespan evolved in part because older individuals transmit ecological knowledge that improves group survival rates. The modal adult lifespan they calculated, 68 to 78 years, is not coincidentally close to the period required to become a master forager and fully capable teacher. Evolution may have calibrated the human lifespan to match the information acquisition timeline, building us to live long enough to become maximally useful to the groups that produced us. Consider the agricultural transition through this lens. The standard account describes domestication as a process unfolding over thousands of years, driven by climate change and population pressure and fumbling experimentation. But this account contains an unexplained tension. How do you conduct multi-generational experiments in plant domestication if no individual lives long enough to see more than a fragment of the process? With elders who had watched the same landscape for 50 or 60 growing seasons, the answer changes. An elderly woman who had spent her entire life in the same valley had seen which patches of ground produced reliably across wet years and dry ones, noticed which stands of wild grain nearest the water source showed different characteristics from those further away, observed which seeds from which plants produced the most vigorous new growth when conditions were right. She could teach this, and what she taught could be refined by the next generation of elders and refined again by the generation after that. The slow experimental process of domestication, 10,000 years of gradual modification of wild species into agricultural ones, begins to look less like a lucky accident stumbled upon by short-lived primitives and more like deliberate intergenerational curation conducted by communities that understood, at least practically, if not abstractly, the value of what their oldest members carried. This requires a conceptual inversion the standard narrative has resisted making. We have consistently thought about elder survival as an output, a luxury that prosperous, stable communities could afford to produce. On this view, societies first became successful enough to generate food surpluses, and those surpluses enabled the elderly to be sustained rather than left behind. Elder survival, on this model, is the consequence of success. The evidence suggests the causation may run the other way entirely. Elder survival was not the reward for success, it was a precondition of it. Communities that kept their oldest members alive and functioning had access to information that communities losing their elders in their 40s and 50s simply could not possess. They made better decisions about seasonal movement because someone remembered the last drought and where water persisted. They treated illnesses more effectively because someone held accumulated pharmacological knowledge that 30 years of observation had made reliable. The burials examined across this film, the grinding stone placed beside the man in Portugal, the 80 animal teeth adorning the shaman of Bad Durenberg, the richest grave goods in the Netherlands field going to the oldest women, were not charitable gestures made by communities wealthy enough to honour their aged. They were evidence of communities that understood, in the most practical and unsentimental terms imaginable, exactly what they were losing when an elder died. What you bury with someone is a statement about what they were worth. And what those communities placed in the ground beside their oldest members says, with remarkable consistency across 5,000 years of material evidence, what they were worth was everything. The library burned, every time, and every community that survived built it again, knowing the cost of losing it. So what force in our deep evolutionary history produced human beings who could live into their 60s and 70s in the first place? Most mammals cannot. Most primates do not. Chimpanzees, our closest living relatives, rarely survive past 45 inches the wild, and their post-reproductive lifespan, the years between when females stop bearing young and when they die, is negligible. Ours is not. Human women can spend a third of their lives past the point of fertility. That is biologically unusual, and unusual biological features require explanations. In the 1990s, anthropologist Kristen Hawkes, working alongside James O'Connell and Nicholas Blurton-Jones with the Hadza of Tanzania, observed something the standard evolutionary framework of the time had no clean account for. Post-reproductive women, grandmothers, women past the age of bearing children were working hard, foraging long hours, finding food in quantities exceeding what they and their husbands needed, directing that surplus toward their daughters' children. And those grandchildren, the ones with actively foraging grandmothers nearby, were visibly doing better, gaining weight faster, surviving dry seasons at higher rates. This was the seed of what became the grandmother hypothesis. The formal logic: a woman past menopause cannot increase her reproductive success by having more children. That option is closed. What she can do is increase the survival rate of the children and grandchildren already carrying her genes. Every calorie she gathers and transfers to a grandchild helps that grandchild survive to reproductive age and eventually pass on the same genetic variants their grandmother carried, including, crucially, any variants predisposing toward long life. Over many generations, this creates a selection pressure. Women who lived longer past menopause left more surviving grandchildren. Those grandchildren inherited the tendency toward longer post-reproductive life. Generation by generation, the human lifespan extended not because long life was directly selected for, but because the behavior it enabled improved reproductive outcomes for the entire lineage. It is an elegant mechanism. grounded in direct observation rather than speculation, and it would explain something that had genuinely puzzled evolutionary biologists for decades. Then the data got complicated. Some studies show real grandmaternal effects on grandchild survival, particularly in pre-industrial European populations, where historical records are detailed enough to track outcomes across generations. A study of 18th and 19th century Finnish and Canadian parish records found measurable survival advantages for children whose maternal grandmothers were alive and living nearby. A study of historical German populations found similar effects. These are not trivial findings. They suggest the mechanism is real in at least some populations under at least some conditions. But other studies find nothing, or find that grandfathers matter equally, which the hypothesis handles less easily, or find that older siblings rather than grandmothers are the key support structure for younger children. A 2016 meta-analysis pooling data from multiple studies found only modest and inconsistent grandmaternal benefits across the sample reviewed. Not zero, not conclusively refuted, but not the clean, robust signal that a hypothesis claiming to explain the evolution of human longevity ought to produce if it is the primary driver. The timing problem cuts deeper still. In 2004, Rachel Kaspari and Sang-Hee Lee published an analysis calculating the ratio of older to younger adults in hominid dental samples, spanning from Australopithecines through modern humans in the Upper Paleolithic. What they found was a dramatic increase in older adults appearing only in the most recent slice of their sample, anatomically modern Homo sapiens in the Upper Paleolithic, roughly 30,000 to 50,000 years ago, not a gradual increase, a rupture. In the Upper Paleolithic sample, older adults outnumbered younger adults at a rate approximately 5 times higher than in any previous hominid group. Kaspari and Lee called it the longevity pulse. They proposed that this sudden multiplication of older individuals was the demographic engine behind everything that distinguished modern humans. Culturally, the explosion of symbolic art, refined tools, long-distance trade networks, the acceleration of technological innovation, more older adults meant more living memory per community, more accumulated knowledge in circulation. The longevity pulse on this reading did not follow the cultural revolution of the Upper Paleolithic. It produced it. But if grandmothering drove the evolution of human longevity, if it was the selection pressure that slowly extended our post-reproductive lifespan, you would expect the evidence of increasing older adult survival to appear, gradually across evolutionary time. Instead, the Kaspari-Lee data suggests a relatively recent and relatively abrupt shift, appearing well after anatomically modern Homo sapiens had already emerged. If grandmothering was the engine of longevity, why did it take so long to turn over? In their 2006 follow-up paper, Kaspari and Lee offered an interpretation that quietly unsettled the most straightforward reading of their own finding. They proposed the longevity pulse was not primarily a genetic event, not a biological mutation spreading through the population. Instead, they argued, the dramatic increase in older adult survivorship was most plausibly explained by cultural changes, better hunting technology, more sophisticated social organization, more effective intergenerational knowledge transmission. The biological capacity for long life, on this reading, was already in the human genome before the Upper Paleolithic, waiting. What changed was the environment. Lower violence rates, better food security, more organized social support for the injured and elderly conditions that stopped suppressing a biological potential that had always been present. Longevity is ecologically plastic, a latent capacity present far longer than the fossil record's age distribution would suggest, requiring particular conditions to materialize at the population level. The implication cuts in 2 directions simultaneously. For the grandmother hypothesis, it is not particularly supportive if the biological machinery for long post-reproductive life was already in place before the Upper Paleolithic. Then the gradual selection pressure grandmothering supposedly exerted was pushing against a door already open. But for the broader story of human biology, the implication is remarkable. Nandi, the Neanderthal with one arm and a damaged eye who survived to 40 inches Iraqi Kurdistan, may not have been at the outer edge of what his biology permitted. He may have been at the outer edge of what his environment allowed. Given different conditions, the population he belonged to might have shown an age distribution considerably closer to what Kaspari and Lee observed in the Upper Paleolithic. The gap was not in the genome, it was in the world. The Kaspari-Lee OY ratio itself carries methodological complications that cannot be dismissed. Their threshold for old adult 30 years is almost uselessly coarse as a demographic marker for elder status. The old man of La Chapelle, estimated at roughly 40 at death, clears it comfortably. Nandi clears it too. If the category is calibrated broadly enough that a 40-year old Neanderthal qualifies as old, the ratio is not measuring the kind of extended elder survival that the study's narrative invokes. Trinkaus noted in 2011 that Neanderthals and modern humans may have overlapped considerably more in their upper age ranges than the OY ratio suggests. The apparent disparity, an artifact of threshold placement, rather than genuine population-wide differences in longevity. The sample size problem compounds this. Hominid fossils from the deep past are rare. The Australopithecine sample contained dozens of individuals, not hundreds. A single unusually well-preserved individual, or a site that happened to favour preservation of one age class over another, can move the ratio substantially, and the taphonomic problem sharpens the concern. Older bones, with their reduced density, preserve less well than the bones of younger adults. A sample skewed toward youth might reflect preservation bias as much as demographic reality. 2 decades of subsequent work have produced more sophisticated tools for reading dentalware and better statistical methods for handling small samples. They have not produced consensus. What the field has instead is a precisely stated open question. Did something change in the human genome roughly 30,000 to 50,000 years ago that extended our maximum biological lifespan in a way it had not been extended before? Or were we always biologically capable of living long, and what changed was simply our capacity to survive long enough to use that capability? The bones have been asked this question repeatedly in multiple languages and methods. They have not yet given a clean answer. Pull back from the fossil record. Set aside the dentalware ratios and the taphonomic complications and the unresolved debates about the Upper Paleolithic, because all of that scientific argument is ultimately in service of a single question that has nothing to do with statistics. What did it actually mean, in practice, for a prehistoric community to have an old person still alive? In any community without writing, the oldest living member defines the farthest point in time from which direct, first-person observation can still be retrieved. Everything before the earliest childhood memory of the oldest person alive is, in a practical sense, gone accessible only through whatever oral transmission managed to survive, in the attenuated form that transmission produces. But everything within that person's own lifespan is still available, still vivid, still attached to the specific sensory detail and contextual judgment that distinguishes genuine knowledge from inherited story. When that person died, the horizon contracted, instantly, permanently. Whatever they remembered that no one else had witnessed the flood in the valley 60 years ago, the summer when the tubers failed entirely, the winter that killed the entire northern herd vanished with them, irrecoverable. Extending elder survival extended that horizon, and the communities that managed to do it were operating with a longer effective reach into the past than those that did not. Think about what a 60-year environmental record actually contains. One severe drought occurs on average, roughly once every generation in many temperate and semi-arid landscapes. A person who lived to 70 might have survived too. They would know the specific quality of the dry season wind 3 months before the worst of it, the particular behavior of certain animals registering dropping water table before human senses could. A younger hunter might be skilled, strong, fast, but they were reading a landscape they had known for 20 or 30 years. The elder had been reading the same landscape for twice that long, and the additional decades were not redundant. They contained information the shorter record could not hold. Climate shifts operate over timescales that exceed individual experience. A river that had been predictable for 20 years might shift its flood timing across a generation. A migration corridor used reliably for 30 years might begin to fail as forage patterns changed. None of this would be visible within a young adult's experience. All of it would be visible to someone who had been watching the same territory for 60 years. The elder who survived a severe drought in childhood and lived to see the signs return half a century later was not simply old. They were the community's early warning system. Oral traditions functioned as the transmission mechanism for this knowledge, but their effectiveness depended entirely on the length of the individual lives doing the transmitting. A single long-lived elder could bridge 3 generations of learners. The knowledge they had received from their own elders, tested and refined, and extended across 60 years of direct observation, could be passed to people young enough to spend another 50 years applying and transmitting it themselves. Across 2 or 3 overlapping generations of long-lived individuals, specific ecological knowledge could travel a century or more through continuous living memory, not as a degraded approximation, but as a body of tested, experientially validated understanding, passed between people who knew each other personally and could ask follow-up questions. The 3-0 to 5-0-year acquisition timeline for deep traditional knowledge is not a cultural artifact or a gatekeeping mechanism. It is the minimum time required to observe enough cycles, enough failures, enough recoveries, enough exceptions to the usual pattern, that the underlying structure of a landscape's behavior becomes legible. There is no shortcut. The knowledge exists in the accumulation itself. The man in central Portugal, buried around 7000 BCE with a grinding stone worn smooth beside him, had been someone's teacher, and his teacher's teacher's teacher. The stone marks the end of a line of transmission that stretched back into a past no living person any longer remembered. His community understood exactly what that meant. They put him in the ground carefully, with the object that best represented what he had been. 9,000 years later, the bones still carry the weight of what he knew. Now, consider what this means for the present. The relationship between contemporary industrial civilization and its elders is, by any historical standard, genuinely strange. We have outsourced memory to written records, digital archives, institutional databases that do not require any human being to hold knowledge inside their own mind. The accumulated observation that once had to live in the body of a 70-year-old woman who had spent her life watching the same forest, the same river, the same sky that knowledge is now, theoretically, capturable in a document, a dataset, a searchable repository. But something else has happened alongside the useful transfer. The form of knowledge that takes decades to acquire, not the catalogued facts, not the technical specifications, but the embodied, contextual intelligence that emerges from sustained observation of a complex system across time, has been systematically devalued, not replaced, devalued, because it resists extraction. An elderly woman who has watched a forest for 50 years carries knowledge about that forest that is not the same as the knowledge in a forestry survey conducted in the same location, even a very good forestry survey. The difference is temporal integration, the accumulation of pattern recognition across seasons and years, and exceptional events and long cycles that no single observation captures, and that no database assembled from discrete observations fully represents. We are, as best the evidence can tell us, the first civilization in the history of the species to systematically build a social structure that contradicts the arrangement evolution spent millions of years producing, not by accident, not through ignorance, but through a deliberate reorganization of how knowledge is stored, transmitted, and valued, a reorganization with real benefits, real costs, and one category of human intelligence consistently underpriced relative to what evolution spent building it. So here is what the number actually cost us. Not a rounding error. Not a footnote misread by careless undergraduates for a few decades before the correction circulated. A century-long distortion of the most fundamental question we can ask about our own species. What were ancient human communities actually capable of, and how did they organize themselves to survive? The 3-5-year figure did not merely produce an inaccurate statistic, it produced an inaccurate civilization, an imagined past populated by perpetual beginners, short-lived, knowledge-poor, culturally thin, dying before they had accumulated anything durable enough to pass on. A world without elders. And once you remove the elders from a society, you have not simply shaved years off the population pyramid. You have extracted the organizing center of everything that community knew. The philosophical core of what went wrong is precise. The figure confused a statistical abstraction with a description of lived human experience. Because infant mortality was genuinely catastrophic, accounting for 30 to 50% of all live births before age 5, the number felt right. It aligned with a prior conviction that ancient life was hard, short, and limited. So it persisted. A century is a long time for a mistake to calcify. During that century, historians wrote about prehistoric social organization, assuming communities could never accumulate more than 1 or 2 generations of living experience. Anthropologists modeled ancient decision-making, assuming no individual would live long enough to witness a 50-year cycle in the landscape. Archaeologists interpreted complex artifacts and long-range planning as evidence of unusual conditions rather than the natural product of communities structured around long-lived knowledge-bearers. What the evidence demands we now accept is this. Prehistoric communities were not perpetual beginners. They were knowledge-compounding societies organized around the retention and transmission of experience that only time can produce. The evidence is real, and the evidence is contested, and both of those things are simultaneously true. The osteological paradox means the dead are selected, not representative. Bocquet-Appel means the age estimates carry larger errors than confident-sounding point figures suggest. The bioarchaeology of care means healed disability demonstrates survival, but not necessarily the specific social mechanisms behind it. The Roman data means the correction to the 3-5-year myth is real, but heterogeneously distributed in ways that simple averages obscure. The Roman evidence comes predominantly from urban populations, from sources that preserve the deaths of the literate and the commemorable, from contexts where nutrition and protection from physical labor were better than in rural or enslaved populations. The median age of 66 may accurately represent one segment of Roman society, while substantially misrepresenting agricultural laborers whose bones are less well documented and whose mortality curves may have looked quite different. None of this collapses the argument. The evidence for long-lived, carefully buried, high-status elders appears not at a single site, not through a single method, not in a single period. It appears at Skateholm in Neolithic Sweden, at Franzhausen in Bronze Age Austria, at Manbach in Iron Age Vietnam, at La Chapelle aux Saints in Paleolithic France, in the Netherlands Neolithic burial fields, in the Roman era skeletal assemblages, in the cross-cultural hunter-gatherer data compiled by Gerven and Kaplan. Independent researchers, working with independent samples, using independent analytical approaches, arriving independently at convergent conclusions. The osteological paradox applies to each individual case. It does not apply to the pattern across all of them simultaneously, because independent selection biases operating in independent populations and independent periods cannot all be systematically skewing in the same direction at the same time by coincidence. No single skeleton constitutes proof. The Portuguese elder might have been 48. Nandi might have been exceptionally robust. The dental wear on the Anglo-Saxon samples might reflect diet rather than age. Each individual case is genuinely uncertain at the margins, but the pattern is not uncertain in the same way. The pattern is the argument, and the pattern has held up across everything the field has thrown at it. The conclusions are provisional, and the evidence, understood honestly and held with appropriate uncertainty, still says something that the popular imagination has been getting wrong for a very long time. The maximum recorded human lifespan, 122 years, achieved by Jean Calment, has apparently not changed since our species emerged. That ceiling was available in Neolithic Portugal. It was there when Nandi lay in his Kurdish cave 50,000 years before Calment was born. The biological architecture making a human body capable of surviving for 12 decades was present in the man buried with his grinding stone around 7000 BCE. What changed across history was not our biological potential. What changed were the external conditions determining how much of that potential could actually express itself. Girvan and Kaplan's argument implies that we did not evolve to be long-lived despite the costs of aging. We evolved to be long-lived because long life was indispensable to the communities that produced us. Old age is not a gift of modernity. It is the design. The shaman of Bad Durenberg, buried with 80 perforated animal teeth and the wing bones of a crane and a headdress assembled from the materials of the natural world, she had spent her life learning to read her community, dressed her body in the symbols of her knowledge because those symbols were the only record they had of what she had known. The elderly women of Neolithic Netherlands, given the richest grave goods in the burial field, interred as holders of something the community valued more than youth or physical strength or reproductive capacity. The old man of La Chapelle, kept fed and alive and eventually buried with care in a rock shelter 50,000 years ago, his arthritis misread for half a century as the signature of an inferior creature. Nandi, sustained across years of accumulated injury by people who had apparently decided that his continued existence was worth the daily cost of ensuring it. In each case, the burial is the community's acknowledgement that something irreplaceable had just left the world, and in each case, the popular imagination, armed with the ghost of a misread statistic, had been erasing those communities from the historical record for generations, insisting they were too short-lived to produce or sustain what the bones plainly show they produced and sustained. The bones in the ground have been trying to tell us this for as long as we have been digging them up. The arthritic hands in Portugal, the toothless jaw in La Chapelle, Nandi's rounded arm stump and his healed ribs and his decades of survival inside a body the environment had every reason to kill. The shaman of Bad Durenberg remembered across 4 or 5 generations until a great-great-great-great-grandson was buried alongside her memory. These were not marginal figures kept alive through charity. They were the cognitive infrastructure of the communities that built them. What you bury with someone is a statement about what they were worth, and the deepest implication of everything assembled here is not about the ancient past. The ancient past is settled, at least in its broad outlines. The elders were there. They lived longer than we thought. They were valued more than we assumed. The communities surrounding them organized themselves in ways that preserved what the elders knew. The question that remains belongs entirely to the present. We are a species whose biology was shaped by selection pressure operating across thousands of generations for communities in which the old were irreplaceable. The maximum human lifespan has not changed. The neural capacity for deep observational intelligence that requires decades to accumulate has not changed. What we are biologically is still what the man in Portugal was, a creature built to grow old, and to carry something in that old age that no younger person can yet possess, and to have that fact matter to everyone around us. We built a different world. Whether that world is capturing the full value of what it took our species millions of years to produce, or whether it is discarding that value in exchange for forms of efficiency that have their own costs, is not a question this film can answer. It is not a question anyone has yet answered convincingly. The bones in the ground say we knew better once. Whether we still do is the question you take with you when this ends.